Hey, what's up, ladies and gentlemen? I'm back with my recorder working, and I'm here today to teach you about inverse matrices and how to solve equations using inverse matrices. So when we taught you about determinants, kind of it was a prelude to having to solve equations using inverse matrices. But so this is going to be a little bit of a loaded section, but I wanted to start with showing you that if you remember way back when you learned that anything times 1 is itself, and that was called the multiplicative identity, right? It's an identity because 3 times that, 3 times 1 is 3, negative 4 times 1 is negative 4. Any number times 1 is equal to that same number, okay? So there is actually an identity matrix. When we multiply it by another matrix, it actually equals the same matrix. So A times I would equal A, and actually it doesn't matter the order in which you multiply. It could be I times A, and would also get you to be A. Now, a lot of people think that this identity matrix is just a bunch of ones, but it actually isn't. It is a column, or excuse me, a diagonal row of ones and everything else zeros. So the 2 by 2 identity matrix is 1 0 0 1. The 3 by 3 identity matrix is 1 0 0 0 1 0 0 0 1. I'll show you that, right? If we have 1 2 3 4 and we were multiplying it by 1 0 0 1, all right, this is a 2 by 2 times a 2 by 2. So the result is another 2 by 2. And to get this top left element, we'd combine the top row with the left column, and it would be 1 times 1 plus 2 times 0, which is just 1. The top right element would be the top row in the right column, which would be 1 times 0 plus 2 times 1, which is 2. The bottom left element would be the bottom row and the left column, which would be 3 times 1 plus 4 times 0, which is just 3. And obviously the bottom right then would be the bottom row combined with the right column, 3 times 0 plus 4 times 1, which is 4, hence giving us the same exact matrix that we started with. So that, and by the way, that would have worked if we flipped them and we multiplied in reverse order. It still would have given us 1, 2, 3, 4. So this is the 2 by 2 identity matrix. This is the 3 by 3 identity matrix. Okay, so you can practice that on any 2 by 2 that you want to. But if there's an identity matrix, then there's also something called an inverse matrix. Because here's the deal: if 6 times 1 is equal to 6, there's something that can take 6 and get it back to 1. And it's not called the multiplicative identity, it's called the multiplicative inverse. 6 and 1 6 are inverses of each other because they get you back to the identity. Just like, what is the inverse of, negative 3? Well, it's whatever you need to multiply negative 3 by to get back to a positive 1. So a negative 1/3 would be the inverse of negative 3, the multiplicative inverse. Well, same way, there is an inverse matrix. If you have 3, 4, negative 5, 1, there is something we can multiply by to get back to the identity here, and that's called an inverse matrix. So I'm going to teach you how to find that. So if A is equal to, if there's a matrix that equal to A, B, C, D, okay, then A inverse is equal to the following. It's equal to 1 over the determinant of what A is, 1 over the determinant of A, times the matrix that you get when A and D switch spots. So D and A go here and here. And B and C don't change spots, but they do change signs. So it would be then negative B and negative C. This is super important to write down. If we have a matrix, A, B, C, and D, we'll call it matrix capital A, then its inverse, which we write in this notation, is 1 over the determinant of A times the matrix we get when A and D switch spots and B and C switch signs. Okay, so let's just verify that real quick. Okay, or let's actually do this. What was it? 3, 4, negative 5, 1. Watch this. Actually, we better start with something. Let's start with something that works a little bit nicer. Let's see. This is just this is just what we've already talked about. So let's do this one. Okay. If we want to find the inverse of S, okay, this is S right here. This is S. So S inverse is 1 over the determinant of S. Well, let's find that real quick. Remember, the determinant of a 2 by 2 is this times this minus this times this. Okay, so 2 times 0, excuse me, 2 minus 0, which is 2. So the determinant of that is 2. So 1 over 2 times the matrix we get when A and D switch spots. So you'd have negative 2. Make sure you guys can see that. Negative 2, negative 1. Come on. And B and C don't switch spots, but they do switch signs. So it'd be a negative 8 down here, still a 0 right there. Okay, and then what you get when you distribute that 1/2, this is now like, this is just scalar multiplication here. You just distribute that 1/2 to everything, and now you get negative 1, 0 still here, negative 4 here, and a negative 1/2. Negative 1/2. The bottom. Okay, so this right here is our answer. That's what S inverse is. It's 1 over the determinant of S times the matrix you get when A and D switch spots and B and C switch signs. Okay, and you could verify that these are inverses of one another by multiplying. Like if you multiplied these two times each other in any order, you would actually get right back to 1, 0, 0, 1, which is cool. So let's just do that real quick just to make sure that happens. If I take, oops. Trying to get rid of this little guy, whatever it is. I don't know if I'm gonna be able to though. Looks like I'm not gonna be able to. Okay. So negative 1, 0, 8, negative 2. Watch what happens when I multiply it times its supposed inverse that we just found. Negative 1, 0, negative 4, negative 1/2. Okay. So that's another 2 by 2, obviously. And let's see, the top left element is the top row combined with the left column. So negative 1 times negative 1 is 1, plus 0 times the negative 4, still 1. That's what we're supposed to start with, right? We want to get back to the identity here. Okay, let's do the top right element. The top right element is negative 1 times 0, plus 0 times the negative 1/2, which is 0. The bottom left element should also be 0. Let's see if it does. 8 times the negative 1, which is negative 8, plus negative 2 times negative 4, which is positive 8. Negative 8 plus 8 is 0. And lastly, bottom right element combines the bottom row here, right column here, and you can easily see 8 times 0 is 0, plus negative 2 times negative 1/2, it's a positive 1. That's what we wanted, right? The two multiplied together get us back to the identity. Okay, now, why is this important? Why do we care about this? Well, we can solve matrix equations in this way, okay? So solving a matrix equation, like if x, this is like, okay, if 3x equals 12, and these are just numbers, it's super smooth. Just divide by 3, which is 4. But really, when you're dividing by 3, you're multiplying by the inverse, right? 1/3 and 1/3. Well, there is no such thing as matrix division. There is only matrix multiplication or multiplying by the inverse. Okay, so here's what we're going to do. We are going to find, all right, if we want to know, okay, 1145 times some matrix x, it's a matrix, equals 2, 3, negative 1, 6, and we got to find out what that matrix is. Okay, well, here's what we're gonna do. We're gonna get rid of we're gonna get rid of this matrix right here, um, and then or just have it be the identity, and the identity times x is just x. So we need to like strip that 1145 away, and the only way to do it is to find its inverse. To find its inverse, multiply both sides by that inverse, and you're going to see it disappear. All right, I'm going to show you that. But first off, let's find that one's inverse, which is 1 over the determinant, right? 1 over the determinant, which is 1 times 5 minus 4 times 1, which is 1. Thank God, that's easy. So 1 over 1 times the matrix we get when A and D switch spots, so 5 and 1, and B and C switch signs, so negative 1, negative 4. Okay, so the inverse here is just 1 over 1 times that. So that's actually what we need to multiply by. So I'm going to write this out. And we actually are going to do it on the left side. Remember, multiplication is not commutative with matrices. So I'm going to multiply this, back up. I'm going to multiply it by this on the left side here, and I'm also going to multiply it on the left side here, because this is an equation, and we've got to do the same thing to both sides. But I'm going to make sure it's on the left of both of these equations, okay? So watch this. 5, negative 1, negative 4, 1, and is that original equation? 1145. Went there. And then I had my x. Better make this a little bit smaller to fit this all on one page. Okay, and that now is equal to, all right, that same inverse that we found, 5, negative 1, negative 4, 1, times 2, 3, negative 1, 6. So I found the inverse of this matrix. I left multiplied both sides of this equation, and if you do the math here on matrix multiplication, you're going to see that this becomes a 1, 0, 0, 1, which it should have, times x, which is just x, by the way. Any inverse time, or any identity times a matrix is just whatever that matrix is. Okay, and then on the right side, let's do that math. This is another 2 by 2. And pretty easy to calculate this. Top left element is top row mixed with left column, which is 10 plus 1, which is 11. Top right is top row mixed with right column, so 15 plus a negative 6, which is 9. Bottom left is negative 8 plus a negative 1, which is negative 9. And bottom right is bottom row mixed with right column, negative 12 plus 6, which is negative 6. Okay, this is the matrix. Remember what we were trying to do in the beginning problem. We're trying to find out the matrix that goes there to create this. And you can't just divide like an equation. You have to find the inverse and left multiply both sides in order to find it. Okay, now about to let you go, but if you remember in the beginning, like we have a 3 by 3 identity, and so there's your 3 by 3 identity right here. Is there a way to find the inverse of a 3 by 3 matrix? Yes, but it's ridiculously hard by hand. So I would only, if we were in class, I would only show you how to do that via a graphing calculator or Desmos, or there's websites out there to do it. But there is a such thing as 3 by 3 inverses. It's just stupid to try to find them by hand. Right? It's not even worth our time. So today you're going to be finding inverses of 2 by 2s, or not today, I guess tomorrow when your homework comes out. Finding inverses of 2 by 2s. You might be doing some multiplying of a 3 by 3 identity times another 3 by 3 to make sure it just gives you what that original 3 by 3 was. But the inverses of 3 by 3s you won't be asked to calculate by hand. We'll only be working with 2 by 2 inverses and solving matrix equations when they have 2 by 2s, okay? We are only down to one more week after this, and I'm going to show you how to solve actual equations with x and y and variables and stuff, setting up matrices and using inverses and stuff. But for now, I just want you to understand that there are these identities out here. There is a way to find an inverse of a matrix. Okay, 1 over the determinant of A times the matrix we get when A and D switch spots and B and C switch signs. And we use these inverses to undo matrices when we need to strip them away to solve, in what we refer to as a matrix equation. Okay, so for now, enjoy that worksheet. Will come out tomorrow. Do the best you can. Talk to you Thursday. All right, bye. Bye.